Greetings and welcome back. Today we're going to be looking at nucleophilic aromatic substitution. And nucleophiles, as you remember, are molecules that will come in here and kick off a leaving group. So in nucleophilic aromatic substitution, we can start with a benzene with a leaving group and end up with a benzene with some nucleophile attached. Usually something like, OH minus or something like that. But this is nucleophilic aromatic substitution. Unfortunately, there is no SN2 at sp2 carbons. Therefore, this is a relatively complicated mess, and it requires pretty extreme reactions to make happen. So electrophilic aromatic substitution, which is what we've done for the last 4 or 5 lectures, is by far the most common substitution on benzene rings. Nucleophilic aromatic substitution doesn't work great. We have 2 ways to get it done, but most of them, like I said, require fairly specific and fairly extreme circumstances. We're going to start out with what's called addition elimination. All right, none of this is SN2, so therefore it all needs to happen in multiple steps. And in addition elimination, it requires an electron withdrawing group. I'll tell you what that is in a second. Electron withdrawing group, either ortho or para to the leaving group. So in this case, I will draw a benzene ring that has a leaving group attached. So we'll put a chlorine up at the very top. And we'll put in an electron withdrawing group, ortho to it, so we'll put in an NO2. An electron withdrawing group are anything that pulls electron to themselves, and those are mostly those kind of deactivating groups. So an NO2 is a good one, a C triple bond N, a nitrile, a carbonyl, or you could kind of have an N+, which would be a nitrogen with 4 bonds. Alright, and what all of those do is that very first group here, that nitrogen is plus, that carbon is mostly plus, the carbon in the carbonyl is mostly plus, and that N is plus. These guys all kind of pull electrons towards themselves, and what they're going to do in this case is to stabilize the intermediate. So we'll start with this guy and we'll add in some hydroxide. Hydroxide is, of course, a pretty good nucleophile, right, OH minus. And what that guy will do is it'll attack the carbon with the leaving group. But you can't do an SN2 reaction here. It can't backside attack that or anything like that. So what needs to happen is that it's actually going to kick off the double bond, and it kicks the double bond over to the carbon with the electron withdrawing group attached. So we would have an intermediate which would have both the OH and the Cl attached to the same carbon. Our intermediate here, unlike electron or electrophilic aromatic substitution, here we're going to have an intermediate that has a negative charge because we have pushed electrons over to that carbon. This is where the electron withdrawing group is helpful. The electron withdrawing group is pulling electrons away from that position. So it stabilizes a C-. It pulls electrons away from that carbon. Since that carbon has extra electrons, it kind of makes it a little bit more stable. And the second step, what would happen is that negative charge would essentially come back over there and kick the chlorine off, and that would give us our product, which would have an aromatic ring restored. You would still have the nitro there, and the chlorine would be gone, and you would have the OH. So if you look at overall what's happened, the chlorine is gone and replaced with the OH. Our nucleophile came in and kicked off the leaving group. As odd as it might be to look at this now, this is very analogous to a reaction we've done already, which would be this one. If you had a nucleophile come in here, remember what happens is the nucleophile attacks that carbon, kicks electrons up to the O. Well, we don't have an O here, but we do have a different place that has a kind of stable location for a negative charge. This was that slingshot mechanism where we would then have an O minus remember the electrons came back down, kicked off the leaving group. We ended up with a nucleophile in place of our leaving group. So hopefully you can kind of pause this, look back and forth at those mechanisms. You'll see that they're almost exactly the same thing. We're bringing electrons in, kicking electrons up, right? Bringing electrons in, kicking electrons up. Then they come back down and kick off the leaving group. They come back down and kick the leaving group off. So that's called addition-elimination, because in the first step we're adding something on, and in the second step we're eliminating something afterwards. You need to have that electron withdrawing group in order to make the C- relatively stable. So if it's here, which is ortho, it's good. If it's para, you can have the intermediates where you can move that negative charge around in resonance. If it's ortho or para, there is a way to stabilize the negative charge. The second way to do this is called elimination addition. And in this case, we do things the other way around. Elimination addition does not require any other group on the bond or on the molecule, but it requires you to get up to about 350 degrees Celsius, which is really, really, really hot. All right, so here's how this guy happens. If we start off with, we'll put a bromine on there, start off with something like this, and let me draw on my H's, because they matter in this case greatly. This is elimination addition. So the first thing that's going to happen, if we put in our, let's say we use sodium hydroxide again, our OH minus, is that we're going to get elimination first. So we essentially get an SN2 reaction. Grab the hydrogen, make another pi bond, kick off the leaving group. Well, hopefully you see why this is so absurd. We would generate an intermediate that had what looks like a benzene ring, but it's got a triple bond instead of a double bond on one of those locations. It is horrendously unstable and would only exist at really, really high temperatures, and that's why you need about 350 degrees to do this. So that is actually called benzene, because it has an alkyne in it instead of an alkene. Well, as you can imagine, that guy is going to be pretty reactive. So we're going to have this in some aqueous solution as well. And the benzene would go off and grab a hydrogen, and that would give us a double bond again. Right? So it would just be an addition reaction at this point. You would have an H and then a plus charge over there. And I'll draw in all my other H's again. And since you have a plus charge, now your OH minus would just attack it. And that would give you your OH attached in actually either the same position or one position over from where you started, but we would once again have performed a substitution reaction with a nucleophile, where our nucleophile, our OH, is in place of our bromine. It's not always at exactly the same place, because when you form this triple bond right here, there is really not a lot of preference. The hydrogen could either go here or there. So you'll get an OH though, you'll get your nucleophile on one of those two positions. So this is an elimination addition, because in the first step you do elimination, and then you add on to the triple bond with your nucleophile. That's how these two are different, is one goes with addition first and one goes with elimination first. But in either case it's not SN2, and in both cases you do get a replacement of a nucleophile for a leaving group. You notice that we had no other way to put an OH onto a benzene ring, so these two things kind of fill the niche of if you want to add on an OH, you can't do it with an electrophile, you have to do it with OH as a nucleophile. So both of these kind of require some other things to happen. In this case it's 350 degrees Celsius, which is, I think, as high as you guys make your sand baths sometimes, but higher than our thermometers go, if that gives you an idea. And the other one requires you to have electron withdrawing groups at very specific locations on that benzene ring as well. All right, thank you very much, and I will see you in class.